Hello everyone, my name is Adhitha. I am a PhD student at Purdue University. In this talk, I will be presenting our work on SparseLNR, accelerating sparse tensor computations using loop-nest restructuring. This is joint work with Krish, Charitha, and my advisor Milind Kulkarni at Purdue University. Tensor computations are an important class of computation used in many domains. They are used in machine learning and many other science and engineering fields such as quantum chemistry, computations related to general relativity, many data analytics calculations, and any application that uses linear algebra. Now, let's see what is a tensor and look at some of the examples of tensor computations. Tensors can be scalars, one-dimensional vectors, two-dimensional matrices, three-dimensional or higher-order tensors. Tensor contractions are a class of tensor computations. You can see some of the examples of tensor computations denoting matrix multiplication, Hadamard product or element-wise multiplication, tensor times matrix multiplication, and matricized tensor times Cartwright product. Let's consider the matrix multiplication of two tensors. For now, let's keep all the tensors as dense tensors so that we don't have to deal with the complexities associated with sparse tensors. I will explain what sparse tensors are later in the presentation. You multiply B with C and sum over the index J can be written using the tensor algebraic notation as shown in the left side of the slide. We can write this matrix multiplication kernel using three triply nested loops, I, J, and K. The overall time complexity of this kernel would be O of ijk, where I, J, and K represent the dimensionalities of the dense tensors. Now, let's consider a little bit complex tensor computation. This example shows doing a matrix multiplication of C and D, then doing an element-wise multiplication with the results of C multiplied by D with B, and then performing another matrix multiplication with E. This computation can be performed using an iterator with four perfectly nested for loops I, J, K, and L. The overall time complexity of this computation would be O of ijkl, again where I, J, K, and L represent the dimensionalities of the tensors. We can break down the complex tensor expression to multiple smaller tensor expressions so that the overall time complexity of the entire computation is reduced. However, this introduces temporary tensors to hold the intermediate results of the individual computations. Requirement to store T can lead to bad cache behavior. This kind of computation can be thought of as executing small kernels separately such that the overall time complexity is lower, whereas the compute code with the four perfectly nested loops could be thought of as a fused version of the smaller kernels such that the time complexity of the compute code is high but does not use any intermediate tensors to store the intermediate results and directly stores the results in the output matrix. In other words, the first version we discussed has bad time complexity and uses less additional memory, while the second version we discussed has good time complexity but high additional memory usage. We saw that the time complexity of the fused kernel with the perfectly nested loop is high and that it does not use any intermediate tensors to store intermediate results. Also, we saw how we can perform a sequence of separate smaller kernels so that we can obtain the results with a minimal time complexity using intermediate tensors to store the intermediate results. However, it is possible to find another solution or a compromise between the solutions we discussed such that the time complexity is low and at the same time using minimal temporary memory to store intermediate results. This can be achieved by fusing kernels. The compute code shown on the slide performs the same computation now with only using a scalar intermediate and with the time complexity of O of ij k plus L. There are several other ways of writing the fused compute kernel, and only one way of fusion code is shown here. Now let's make the B tensor a sparse tensor. Here, the first kernel refers to the sampled dense-dense matrix multiplication, where we have a dense matrix multiplication of C and D, but then it's sampled by the sparse matrix P. Notice that the sparse matrices are in bold here. The second kernel refers to sparse matrix multiplication. These two kernels are two key kernels in graph neural network or graph embedding networks, and in some instances, they are executed back-to-back in graph embedding workloads. Now we ask the question, can they be fused when we have sparse tensors and non-affine loops in the computation? There are several challenges associated with fusion when it comes to sparse tensor algebra. On top right, you see how you would store the matrix on the left using a dense array. On bottom right, you see how you would only store the non-zeros of the matrix and omit the zero values of the matrix. There are several compressed formats like the one shown in the slide used to store sparse tensors: compressed sparse row format, compressed sparse column format, coordinate format, compressed sparse fiber format, etc. Sparse tensors are irregular data structures. Therefore, they do not allow random access and hence cannot rewrite accesses. Having sparse tensors in tensor computations leads to compute code with non-affine loops, and also we cannot permute or reorder sparse loops in any arbitrary order we like to generate code. Generating code for sparse tensors requires new techniques to deal with these complex irregular data structures. We have a case where we can have a single kernel with perfectly nested loops which does not require temporary memory, but they have bad time complexities for complex tensor expressions. We have a case where we can have many smaller kernels with good time complexity, but they have bad memory usage with bad cache behavior. By using kernel fusion, we can achieve the best of both worlds. Fusion is well studied for dense tensor algebra. Frameworks like polyhedral framework brings forth ways of fusing dense kernels. But fusion of sparse tensor algebra kernels is not fully studied and hence remains an open problem. Therefore, we introduce SparseLNR to solve part of this open problem. The Taco compiler is specialized for sparse code generation. It has three main components to define the computation: the tensor algebra language, the data representation language, and a scheduling language. Once the user defines a computation, it can spit sparse and dense loops following the instructions given using these three languages. We will briefly discuss what these individual components are later in the presentation. There are three main contributions in our work. 1. We introduce branched iteration graph, a novel representation for sparse iteration spaces. 2. We have a new scheduling primitive that the programmers can use to invoke the transformation for loop fusion after distribution that generates a branched iteration graph. Finally, we changed Targo's transformation to support our new loop restructuring transformation, and we adapt Targo's code generation strategies to the branched iteration graph, allowing us to generate sparse iteration code. Before going into our new scheduling transformation, let's briefly look at the components of Targo. You can use the tensor algebra language to define the actual operation. You can define the type of the tensors in the computation using the data representation language. There are different sparse data types like compressed sparse row, commonly known as CSR, compressed sparse column, commonly known as CSC format, or coordinate format, etc. Then you can use the scheduling language to unroll loops, reorder or permute loops, split and collapse loops for load balancing and parallelization. You can navigate through many schedules and pick the best schedule that works for your computation. It uses an intermediate representation called iteration graphs to define the basic loop structure of the computation, and uses merge lattices to generate sparse code using the iteration graph. Please read the original Taco compiler paper for more information on how everything works. Now, let's consider our sparse tensor kernel example, the combined sample dense matrix multiplication and sparse matrix multiplication. Notice that the tensor B is sparse here, and let's assume its format to be of compressed sparse row format. For this sparse tensor computation, we can generate an iteration graph as the intermediate representation. Notice that I have used a slightly modified version of the example by using the transpose of D matrix here. The reason to do this is because if I use dkj, then the iteration graph generated by default would have the order of I, k, j, and l instead of the ordering I, j, k, and l. I will later show an example of what happens if we use dkj instead of djk here. You can see we have nodes for indices I, j, k, and l in the iteration graph, and there are edges denoting how the tensors access these indices. Now the code generation algorithm can generate loops for each index, and this computation has a time complexity of O of non-zero values of b into kl. Now to begin our transformation, we try to remove tensors from the back of the tensor compute expression. In this case, we try to remove E tensor from the expression. We see that E goes from indices j to L, and that L is shared only by E and the output tensor A, in which case E can be safely removed from the original tensor expression. Since E is going from j to L, now in the new tensor expression, the output tensor must have indices I and j. These indices can be inferred by way of construction of the original tensor expression. We remove E and get the new tensor expression and new iteration graph for the new expression. Now, the tensor expression we get is analogous to the SDDMM kernel tensor expression. We call this tensor expression producer expression. And if we were to generate code for this kernel, it would have I, j, and k triply nested loop with time complexity of non-zero values of b into k. The next step of the transformation algorithm is to add back the removed tensors into the new output from the previous step of the algorithm. Then we get back the SPMM tensor expression in the original combined tensor expression. We call this tensor expression consumer expression because it consumes the output of the producer expression from the previous step. The code of sparse matrix multiplication would have a triply nested loop, and the time complexity of this kernel would be non-zero values of b into L. Now, we look at the producer expression and the consumer expression separately. If we run these kernels separately, we would have a lower time complexity compared to our original execution. To continue with the transformation, we run a pointer from the top of both the producer iteration graph and the consumer iteration graph to identify the common indices shared by the producer expression and the consumer expression. And we save these indices as common indices to create the branched iteration graph. And also, we mark this point in the graphs as the nest boundary, which is again used to create the iteration graph. Please look at our paper to read on the usage of the nest boundary. Now, we run a pointer again starting from the nest boundary to the bottom to identify any common loops after the nest boundary. In this example, we see that there are no common indices after the nest boundary, so we leave that empty. At this point, we are ready to generate the branched iteration graph. As the final step, we combine the common loops and keep the graph sections below the nest boundary as the producer and the consumer separately. Common indices after the nest boundary is used to define the bounds of the scratch memory going from the producer to the consumer. Please read our paper for a more formal definition of the branched iteration graph. Note that this transformation can be used recursively if applicable to the given complex tensor expression. Using this branched iteration graph, we use Tarko's sparse code generation to generate the sparse loop for the computation. Let's look at another example where we use our original example of sample density matrix multiplication followed by sparse matrix multiplication. We use dkj here instead of djk as compared to the example we discussed in the previous slides. We start with an iteration graph with index ordering of I, k, j, and l. Now we can follow the same procedure as before. We get the producer graph from the original iteration graph. Then we generate the consumer graph. After that, we can identify the common indices from the top of the producer and consumer graphs. At this point, we can identify the nest boundary for the producer and consumer graphs. By looking at the indices below the nest boundary, we can identify that the index j is the common index below the nest boundary. We save it so that we can use it for the creation of the branched iteration graph. Now, we generate the branched iteration graph using the producer and the consumer graphs. Notice that the common indices below the nest boundary contains the index j. Therefore, a vector of the same size as the dimension j would be added to share the results between the producer and the consumer. Notice again that the vector which is of the same size as the dimension j added to share the results between the producer and the consumer is same as the common indices below the nest boundary. The outermost loop I is same as the common indices from the top, and these are one-to-one correspondences used in generating the branched iteration graph and to generate the dense and sparse loops. However, it is possible to arrive at the same branched iteration graph as the previous example. To do that, first, we can reorder the loops in I, j, k, and l order, and then apply the loop nest restructuring algorithm. This example shows how different loop permutations can lead to different loop nest structures for the same kernel. We compare our results with the kernels generated by Tarko. The comparison is twofold. Tarko original stands for the version of the kernel where we evaluate the combined tensor expression with high time complexity. Tarko separate stands for the version of the execution where we take the tensor expression from the Tarko original version and manually break it to smaller kernels. And when there are multiple ways to break down the kernels, we evaluate all of them. We evaluate 6 benchmarks. The first one is sample dense matrix multiplication followed by the sparse matrix multiplication. The second one is sparse matrix multiplication of the Hadamard product of 2 dense matrices followed by a matrix multiplication. Third, sparse matrix multiplication followed by a dense matrix multiplication. Fourth one is a combination of the first and the third benchmarks. The fifth benchmark is metricized tensor times Katrirawa product followed by matrix multiplication. And the last benchmark we evaluate is sparse tensor times matrix multiplication followed by another sparse tensor times matrix multiplication. We evaluated the benchmarks on a 64-core machine and reported the performance of both single-thread and multi-thread executions. If the kernels in the benchmarks were available from the previous works of Taco, we used them in our evaluation. When they are not available, we evaluated multiple schedules and selected the one that gave the best performance. We evaluated the benchmarks on real-world 2D graphs and 3D tensors from the Soot Sparse Matrix collection, the network repository, Frost dataset, and a dataset from 1998 DARPA intrusion detection evaluation. Now, let's see SparseLNR's performance against Taco separate and Taco original executions. In general, the speedups we see against the Taco original comes from the reduction in time complexity. We see this behavior in both single-threaded and multi-threaded executions. The speedups we see against the Taco separate comes from not using a large temporary tensor and cache benefits. We see the same behavior in both single-threaded and multi-threaded executions. The slowdowns with respect to the separate version comes because sometimes there are other optimization directives that could be used when the kernels are smaller and does not have a loopness structure. Therefore, we could fine-tune the optimizations. We see slowdowns especially when the intermediate tensor in the separate version is small. For large tensors with a large number of non-zero values, we see better performance in SparseLNR. SparseLNR scheduling directive can be applied recursively. Comparatively very large speedups we see for the benchmark SDDMM, SPMM, GEMM comes from the accumulative time complexities introduced by the perfectly linear loop nesting structure in the Taco original version. We evaluate the separate version of the Sparse TTM in several different ways. The reason we see slowdowns in the separate version of the Sparse TTM benchmark comes from the low dimensionalities in one of the three-dimensional datasets. Please read our paper for a more detailed discussion on the evaluation of the results. The slowdowns we see with respect to the MTTKRP GEMM benchmark happens when the intermediate tensor in the separate execution is small, such that it can fit in the last level cache. But we see better performance in using SparseLNR when the intermediate tensors are large. In summary, different versions perform well in different scenarios with varying dimensionalities of the sparse tensors and dense tensors. Performance is also dependent on the sparsity pattern of the sparse tensor. It is not always possible to come up with one good schedule or a template schedule that is good for all combinations, sizes, and sparsity patterns of sparse and dense tensors. That is why it is important to have SparseLNR kind of loop nest restructuring schedule so that it can be used when applicable to achieve the best performance. Now, let's see how SparseLNR scales with increasing number of threads. We see good scaling in SparseLNR and Taco separate versions for the STDMM SPMM benchmark. SparseLNR delivers comparable scaling to the best alternative approach. We observed similar scaling results for other benchmarks and datasets. Now let's see how SparseLNR behaves with varying dense dimensions in the SPMM, GEMM kernel. We change K and L inner dimensions of the benchmark to see the varying performance of SparseLNR with respect to Taco separate and Taco original. We generally see that the SparseLNR performs better with increasing K and L dimensions. but the performance starts to degrade as the dimensions get too large, because the temporary in the SparseLNR version of the code gets large enough that the temporary and the input arrays start to get evicted from the caches. SparseLNR gives the best performance within the area highlighted. Please read our paper for more details on the evaluation. In summary, we can say that sparse loop fusion or loop nest restructuring is a performance-critical optimization. Current automated sparse code generation techniques do not support loop fusion that requires imperfect loop nesting. We propose a novel method for restructuring loop nests in the context of sparse tensor algebra computations. Our transformation shows good performance on various real-world datasets and benchmarks. If you have any questions, please forward them during the question and answer session at the International Conference on Supercomputing 2022 or contact us by email. Thank you for listening to the presentation.